All right. Got a lot of background noise for some reason. What's going on here? Okay, so anyway, today we're doing the lab for chapter 6 or lab 6. It's called Compounds and Their Bonds. I've got my little kit here to kind of walk through some of this stuff with y'all. So you should have done the pre-lab discussion video already where Jamie kind of walks through some of these concepts. For those of you in my lecture course, I did a long lecture today and also provided a lot of videos, which I think I did in the labs as well, a lot of extra videos that touches on some of the concepts that you're going to need to know to do this. Today we're focused on ionic bonds and covalent bonds, molecular bonding, all of these different terms for chemicals and how they connect with each other. Okay, so let's look at the lab manual and kind of see what we got to do today. So where was it? Internet. I posted the lab manual under content for lab 6, compounds and their bonds, lab manual. Okay, so we are leaving out one portion of it. Which portion? Pre-lab discussion, PowerPoint. Was it this one? Nope. Pre-lab discussion PDF document. I think it's this one. So make sure that we're not doing number 1, anything to do with the electron configuration and the electron orbitals. So like the S, the P, and the D orbitals. So number 1 and number 4 on part A. And then what else? It looks like that's it. Okay, so this is a dry lab, meaning that you do everything on your own. Typically, you'd be in lab and we'd have these little model kits. Let me go back to me. These little model kits where we'll build these little molecules and you'll kind of reinforce what you've learned in lecture. So you will not have access to all of that. I'm going to go through and kind of do a couple examples and show you how we use these and why we use them. But all of the concepts are stuff that you should have pulled from lecture. So I'll try to kind of reiterate some of those things as we run through the lab. But if you have problems with anything in particular, you want to go back and check out the lecture or your notes, the text, possibly some YouTube videos. Like I said, I provided some of those as well. And just touch on the things that you need to strengthen in order to be successful at this portion of the course. All right. So a lot of it is based on the valence electrons. So being able to recognize those and do those is very important. We'll also be doing Lewis dot structures. So those are based on the valence electrons. So that's why you need to know valence electrons to be able to do Lewis dot. And you need to be able to do Lewis dot to do VSEPR and the shapes of the molecules. Okay? So one thing leads to another, and you got to kind of make sure that you know your fundamentals before you go on to something more difficult. So now, let me go to the lab manual and let's kind of walk through what you're going to do for this lab. So I mostly caught up on the grading. Some of you emailed or submitted your labs in different ways. Those are still being worked out. I've gotten a lot of those caught up, but some of those still have to be done as well. But no worries. I'm working on the test. I'll get those back to you. I still have a couple people that haven't taken it. So I'm sorry. It kind of puts everybody in a bind because I'm not going to release the answers until I know that everybody's completed the exam. So by this Sunday, either those that haven't done it will get a 0, or everybody will be turned in, and I'll have them posted on Monday. All right. So Jamie should have went through, or she did go through a lot of this in the pre-lab discussion. This little chart is very important. It's called polyatomic ions. You'll need to be able to recognize those and pull them out. Use their different charges to be able to determine what they're hooked to. Okay? So remember, the atoms typically follow what we call the octet rule, where they have 8 electrons around its outermost shell. And we fill this out by forming bonds where electrons can be shared between atoms. So if I notice here on this NH3, oh gosh, I'm on your lab manual. I'm just kind of scrolling through. Jamie, like I said, Jamie went through all of this, but I want to kind of touch on a couple more things. So be able to determine the number of valence electrons. You can do that with your periodic table, correct? Whichever group it's in is the number of valence electrons. Especially true for the far left and the far right. So everything in group 1 has 1 valence electron. Everything in group 2 has 2 valence electrons. When I go over to group 3, I skip all the way to boron, start here, 3, 4, 5. Everything under oxygen, sulfur, selenium has 6 valence electrons. Now this is not necessarily true for the metals, okay? You will need to be able to determine their valence electrons either by what they're connected to, or if it has a Roman numeral behind it, that tells you how many valence electrons it has, okay? So back to lab. All right, so let's take, for example, magnesium. Magnesium has 12 electrons total, but that doesn't really mean anything for valence. So number 12, magnesium here, valence electrons 2. It has 2 valence electrons. So when I lose those electrons in an ionic bond, it becomes Mg2+. Okay, so if you're unfamiliar with that, you need to go back to the lecture. I'll post my lecture on here as well. It's kind of long, but if you want to go through there and kind of see what we're talking about. So the Mg2+ combines with 2 Cls, each of which have a 1- charge. So you're making sure that the charge is balanced on each side. I have 2+ on the left side. I want to have 2- on the right side because it needs to balance out to 0. No charge. Cl typically has a 1- charge because it's a halogen with 7 valence electrons, and it typically picks up 1 valence electron from the magnesium in this case to make a 1- charge. So it takes 2 of the chlorines to add to 1 magnesium to balance the charges. Okay, here's what I was talking about with the Roman numerals. So if you see a Roman numeral, that's telling you what the charge of the molecule is, or how many valence electrons it has. So iron 2 is Fe2+. So if I connect iron 2 with chlorine, I'm going to need 2 chlorines to balance out the 2 positive charge on the iron. Okay, if I have iron 3+, then I'll need 3 chlorines because each chlorine has 1 negative charge. So 3 chlorines will balance out the 3 positives on the iron. So that's how you use these other atoms to determine your compound, how the metal combines with your compound. Okay, so that should be pretty self-explanatory there, but I am going to do some problems once we get to the lab. Okay, polyatomic ions are just their own little set of molecules that kind of exist within the molecules as a whole. They have their own charges, and so you'll kind of need this chart to be able to do these easily. You could, I mean, at this point, I've remembered most of these, or can remember most of these. But I don't remember them all, so this chart is helpful. Just keep it close by, and then if you recognize something from this chart, you can kind of section it off and say, oh, well, that's a hydroxide ion. It has a negative charge. It's by itself. Now I can do everything else that I need to do to balance my equation. All right? So, let me see. Where are we now? Okay. So when you talked about your lectures, in your lecture, you should have talked about the difference between ionic bonds and covalent bonds, right? I'm going to go to the text real quick. An ionic bond transfers electrons. So like in the case of sodium and chloride, the sodium has given the electron to the chlorine, and the sodium is one shy, the chlorine is one heavy, but they are still separate atoms, okay? They have separated those electrons. In a covalent bond, you are sharing the electrons. Let me find a picture of one of those. That's polyatomic. Molecular bonds. Let's see. Can't believe they got a picture. Here goes one, fluorine, fluorine. So they share these electrons, all right? Right, in the sodium and the chlorine's case, the sodium gave the other atom the electron, and then they were separate. When I did my Lewis dot structure, I just had an Na with nothing around it, and then on the Cl, I had all 8 individual electrons. Well, when you have a covalent bond, you actually draw out this line bond. Let me get my iPad ready and kind of show y'all some of these Lewis dot structures, because that's what you're going to use to do the VSEPR models, okay? So, get this on, screen mirror, done. Okay, so fluorine here has 7, or typically would have 7 valence electrons around each atom. So fluorine, 1, 2, 3, 4. When you're doing a Lewis dot structure, you do it clockwise and you fill out the number of valence electrons. So I'm at 4. I went in a clockwise motion. 5, 6, 7. Okay, so I have 1 lone electron right here. All right, now I'm going to do another one. 1, 2, 3, 4, 5, 6, 7. I have another lone electron right there. Okay, so now I need to find a way to combine these, fill my octet. Remember, the octet says that every atom wants to have 8 valence electrons. So I need to find a way to make both of these have 8 valence electrons. The easiest way to do it is to combine and share those 2 single electrons. So what that ends up looking like is this right here, a bond in which this line here represents 2 electrons, right, shared together in a bond, and then I fill out my other valence electrons. So 6 around that, 6 around that. If I go and I check for my octet rule, I pretend this has 2 electrons, right? So there's 2 in the bond, and then I have 6 around the outer edge. So 6 valence electrons, V's, valence electrons. And then 6 on this side. So technically, both fluorines are filling their octet. The 2 electrons are shared by both of them, so I can say this fluorine has 8 electrons, and then I can also say that fluorine has 8 electrons. Okay, so that is a covalent bond. We share those by, we share the electrons between them with a chemical bond. So let's do another one. This one is going to be a little bit different. It's oxygen. So the first thing I'm going to do is draw an oxygen atom here, and I'm going to do the Lewis dot structure of oxygen. So I go to my periodic table, and I see that oxygen is in group 6. Okay, so 6 valence electrons. Go back to my iPad, and I'm going to do the Lewis dot structure. So in clockwise motion, one at a time. 1, 2, 3, 4, 5, 6, and never 2 more to a region. You can only have 4 regions: north, east, south, west. It can have more than 4 regions. I shouldn't have said that. in all of these cases that you'll see here, it can only have 4 regions because of the octet. 2 electrons per region. You want to have an octet, so there's 4 regions. That's why we think about it 4 regions. So now I'm going to do another oxygen like we did with the fluorine. 1, 2, 3, 4, 5, 6. Okay, so now I want to get to 8 electrons on each, but I have 2 solos on each one. So maybe I could share those with each other. All right, and so what will end up happening is those 2 will be shared in what we call a double bond. So it's actually 4 electrons are tied up in this, 2 in each line, 2 in that line, and then 2 in this bond. Okay, so there's 4 electrons tied up in this double bond. And I also have to put my valence around the outer shell. Okay, so that is the O2 molecule. All right, I'm going to write the chemical formula right there. O2. If I notice here, this one has 4 electrons, so if I have 4 valence electrons on the outer shell and then 4 within the bond, that means this oxygen fills its octet. Same on this side, 2 there, 4 in the double bond, so that makes 8 total. So that's how you determine how many bonds and whether or not you bond atoms together. Okay? So I'm going to write these out one more time. But now we're going to look at what we call the VSEPR model. So I'm going to let me do 3 different ones. Oh wait, F, and then I'll do another one on the next page. Okay, so something has changed here because I put that double bond in. Anybody notice what has changed? Because I just said it a second ago and I said to stop and I said, no, don't do that, don't do that. There's no longer 4 regions around that oxygen. Okay, if I go through and separate my different electronic regions, we call them electronic domains or electronic regions. Okay, each lone pair of electrons has its own region, and then the bonding area is a region as well. So 1, 2, 3 regions for that oxygen, and then also 3 for this one as well. See, these arrows point out toward the electronic regions. So that means this has, let me come over here and do it again. Oxygen has an arrow, a region that way, and then a region that way. And this oxygen comes back across there and there. Okay? So, let me do the fluorine as well. So let's mark off our lone pairs of electrons. So there's 1 lone pair, 2 lone pair, 3 lone pair, and then the bond. So this one has 4 electronic domains. All right, so when I write this one, I could say this there goes that way, and that way. And then my F over here comes back toward that one, and also has the 3 pointing out. Okay, so each F has 4 electronic domains. This brings me to the VSEPR model. The VSEPR model is a way of predicting shape. Okay, so I'm going to do this one. All right, so you see here on this chart, this is one of the simpler ones, but there's all different kind of charts. Your book has one. This is the one I'm most familiar with. Let me see if I can blow this up a little bit. I guess not. No. See if I can use this one maybe. Yes. Okay. All right, so you'll see these charts do it and they'll word it in different ways. Let me come back here and just give you some of the terms so that you don't get confused if you see it on this thing. Okay, so oxygen, there, double bond O, and there. Okay, so if you see, let's see, it says pairs of electrons, okay? So every electronic domain is a pair of electrons, all right? But the bond itself is only one. Let me see how this is worded. So let's say we have 4 pairs of electrons, one bonding pair, this is not a good example. I don't like this chart. Let me see what the text one looks like. Text, shapes. Okay, I like this one. I like the way this one's ordered better. Let me pull y'all over to this one. Alright, so this is the one from the text. It doesn't have all of them though. I wonder if your lab manual has one. Okay, so I'm looking on the left of this table and it says electron groups. So that's what I want to use when I'm talking about electronic domains. However many number of electronic domains, that's the number of electronic groups. Okay, so coming back to my iPad, I'll say that there are 3 electronic domains around each oxygen. And there's one bonding pair, right, which is right there. All right, technically there's 2 bonding pairs, but when you're talking about a bond, you're just saying that's one domain. If it was a triple bond, it'd still be one domain. Let's do H2O. I think that one will be a little more visible. Okay, so lone pairs there. The hydrogen only has 2 electrons, so it's fulfilled. All right, there is essentially only has 1 electronic domain going that way, so that makes it linear. We don't worry about that. Now the oxygen, on the other hand, has 1, 2, 3, 4 electron groups, as your other chart would say. I say electron domains. And then 2 bonding pairs, one there and one there. So 2 bonding pairs, or yeah, I'll just say BP, bonding pairs, and then 4 electron groups. Okay, so I've done this, and remember I did my Lewis diagram. I came to the determination that I have to form a bond with this H and this H. And so now I'm at this point and I'm trying to figure out its shape. So I go to my chart here, I say 4 electron groups, there's that. 2 bonded atoms, so I come down here to that, and it means I have 2 lone pairs, that's correct. So you could do it either way, right? You could look for the number of lone pairs, or you could look for the number of bonded atoms. And I find out that my molecular shape is bent, and it has a little thing there. Okay, so now let's talk about why that is, and let me show you one of my little models here. Okay, so pretend this is a water molecule. Okay, so I have my 6 valence electrons stacked around there, and I'm trying to figure out what I need to bond with it. I need to bond a hydrogen with one of the valence electrons, and I need to bond another hydrogen with the other. Okay, so I'm going to leave these little sticks on there to represent the lone pairs of electrons, just so y'all know that we're on the same page. This is that same molecule that I drew here. Okay, these little white atoms are the hydrogens, and this blue one in the middle is the oxygen. Okay, those 2 little lone pairs of electrons are represented by these 2 little sticks with nothing on the end of them. Okay, so now the VSEPR model, or valence shell electron repulsion, says that these electrons want to be as far away from each other as possible because they repel each other, right? They're both negatively charged and they push away, just like the North Pole will push away from the North Pole of one magnet will push away from the North Pole of another magnet. You remember you have to have opposite poles for them to attract. If you sit them with the same pole, they repel each other. So that's what's happening here. All of these little gray sticks are very negatively charged electrons. So they push away from each other as far as they can. And that ends up creating this shape we call a tetrahedral. Okay? Now, if this was flat, like flat on the ground, let me see if I have something like that. Not that one. 1, 2, 3, not that one either. Doesn't look like I have the kind of molecule that I need here. I thought I did. I don't though. Okay, I'm gonna pull this off there and imagine this is, let me do this one. Okay, so this one's a little different. This is, let's call it NH3. I'm gonna write this out on here. My dog's getting restless. Now do the valence electrons. So 1, 2, 3, 4, 5 for N because it's in group 5. Then I want to connect it with 3 H's, each of which has 1 valence electron. So this one's easy enough. I see 3 solo electrons by themselves, so I can share those with these hydrogens and make NH3. Okay? And then I have a lone pair up there. So electronic domain, same thing, 4, right? 1, 2, 3, 4. That'll match up on my chart. Number of lone pairs, I have 1 number of lone pairs. So this is going to be trigonal pyramidal. We'll go back to here. 4 electron groups, 3 bonded atoms, 1 lone pair. That'll be trigonal pyramidal. So what does that look like? It's still the tetrahedral. Okay, it's still that same little shape that I have with the water, except for this time I just got the 1 lone pair up here. But basically the concept is that the electron domain, the number of electronic domains, sets the original shape. Okay, then it's essentially how many atoms on there till I figure out the molecular shape. So when it says molecular shape, it's just concerned about the atoms. So this will be bent. Okay, the molecular shape of a tetrahedral with 2 lone pairs, as we saw from water, was bent. Okay, so that's that. The electronic shape is tetrahedral because it has the 4 electronic domains. NH3, which is what we just did on the iPad, has 3 bonded atoms, 1 lone pair. So the electronic configuration, electronic geometry is still tetrahedral because I still have 4 electron groups. But the molecular shape, I don't pay attention to that lone pair, and it's in a pyramid. So we call this trigonal pyramidal. Okay? If I look on my chart, I'll see trigonal pyramidal. There is also trigonal planar, which is the one I was going to show you that I don't have a model for, but it's essentially this, except for no electron domain lone pair, and so that causes these to flatten out. They're not making a pyramid anymore, they're just making a triangle, right? And then a tetrahedral with atoms on every side is still a tetrahedral. Both the electronic configuration and the molecular geometry are both tetrahedral because there are no lone pairs. Okay. Look back at your labs. Where is it at? Lab manual. Let's see what else we need to kind of touch on. So that's the electron dot formula. Naming compounds. So if you're in my lecture, or if you look at my lecture, you'll see that we went through there's a chart that has all of the prefixes for naming molecules, and it's pretty easy. It's just like di, tri, tetra, penta, hexa. There it is. It is on page 186 of your text. 1's mono, 2 di, 3 tri, 4 tetra, 5 penta, so on. Okay? So when you are naming compounds, ionic compounds are easy enough. You just put the cation first, or the metal first, and then the non-metal second. And then you drop the INE and add IDE. So like sodium chloride. Let me see if there's another example up here. Iron chloride, copper chloride, or something that drops it's not chloride. We'll do some examples in the sheets. Okay, so you do have this little chart there, and it only goes up to tetrahedral, looks like, so you might need to look on the internet for one that goes a little further. Okay, so we've touched on most of those questions. You should be good there. Remember, mark out number 1 and number 4. You're not doing that. You are doing the electron dot symbols, whether or not, how many electrons they lose. Let's see, physical properties, blah, blah, blah. Okay, so that's easy enough, right? You know the type of ion it makes is based on whether or not it is on the left side of the periodic table, on the right side. The left side, it wants to give them up. Right side, it wants to accept electrons. If it gives away electron, it's positively charged and forms a cation. If it takes an electron from another atom, it gets negatively charged and is an anion. And then you always name the cation first when you're naming the compound. Okay? And in this case, in ionic compounds, you don't worry about di, tri, any of the prefixes, because it's implied based on either the Roman numeral or the chemical formula. Okay? And so you ought to be able to predict that, right? Chlorine can only hook up to one other atom. So if I have MgCl2, that means I had to hook up 2 chlorines to get rid of 2 electrons from the magnesium, which makes it Mg2+. All right, we'll do an example of that. Or I did an example of that on my lecture. You can go back and check out that. Names of ionic compounds. So you'll go through, you'll name the compound, you'll write out each of the positive and negative ion. So, for example, I'll do the first one with you. Barium is the positive ion. Remember, the positives always named first. So you can pretty much just go through here and put the first one first and then the second one second. I mean, it's that easy. So barium plus, barium, and then F minus. So F is minus. Since there's 2 of them, then barium has to be 2+. Okay? So why is that? Let me go to my iPad real quick. iPad, because I think we did this earlier. Let's see. Fluorine, 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 fluorine. I did, but I covered it up, didn't I? Oh, no, right here. Okay, remember fluorine had 7 valence electrons. So if I'm going to hook up anything to a fluorine, let me erase this. Fluorine had 7 valence electrons. Anything that connects to fluorine is only contributing 1 electron. Okay? So that means however many fluorines I have is how many electrons were contributed. So since I have 2 fluorines, that means that barium had to give away 2 electrons. Okay? So that's how easy that is. And that works for every halogen. So fluorine is a halogen in group 7. Chlorine, bromine, iodine, and fluorine all can only bond to one other atom. There's one exception to that, but I don't think you'll cover it. So all of the halogens only accept one electron. If you see something bound to a halogen, then that means it's only giving it one electron. And so however many halogens you have, that's what your charge is on the other side. So Ba2 plus, F 1 minus. And then so when I write out my thing, it'll be barium fluoride. Instead of barium fluorine, you drop the INE at IDE, barium fluoride. Okay. Oxygen, you drop the YGEN and say ide. So this one will be magnesium oxide. I'm not going to give you any hints to the charges though. Okay, and we talked about going the other way, right? If it gives you the Roman numeral, then you should be able to back calculate based on what this is. So oxygen always has a 2 minus charge. That's why it's combined with an iron 2 oxide. Sulfur is in the same class as oxygen, so it'll always have a 2 minus charge because it always wants to get to the octet. And remember, oxygen is 2 electrons short of an octet. So it typically will take 2 electrons from somewhere else. In this case, iron. Sulfur is the same way, except for it took it from copper. So just to do this one as kind of an example, copper sulfide. If sulfur is S2 minus, let me put this on here. If sulfur is 2 minus and it connects with a copper that the Roman numeral told me it only has a +1 charge, so it's only losing 1 electron is what that means essentially. Only has 1 electron to contribute. That means I need 2 coppers, right? This one has a plus charge, this one has a plus charge. I need 2 coppers to match the 2 minus charge on the sulfur. So that's why I say it's important that you know like the trends. All of the halogens have a 1 minus charge. Oxygen and sulfur both have a 2 minus charge. Nitrogen, which is this nitride here, has a 3 minus charge. Okay? So then you balance the charges based on that information. What's another one I can do with nitrogen? Mg2 plus. Let me do the one that I did in my lecture. Say I want to combine Mg2 plus with N, which has a 3 minus charge, okay? And this is predictable. Like, I know this because of the periodic table. Let me go back to the periodic table. So Mg is in group 2, so it's going to have a 2 plus charge. It's going to want to give up 2 electrons. N is in group 5. It's 3 electrons short of having this noble gas configuration, 8 electrons. So it's going to have a 3 minus charge. So that's how I knew that. And it's, I mean, it's not just something that, like, this is something you can figure out. You don't just have to know. Okay. So now I want to combine these in a way that balances out the charges. So I have to use the least common denominator because 3 doesn't go into 2 and 2 doesn't go into 3. So 6 would be my least common denominator. That means I'll need 2 nitrogens to have, 2 times 3 minus would equal 6. And then I need to have 3 Mgs to get to 6 on this side. Okay? That plus and minus is a charge, not the operation. I'm multiplying this. Okay, so Mg3N2. That's how you use the charges of these atoms to balance out the chemical formula. Okay? So you'll do that back and forth with those. Hydroxide. So this has to do with those polyatomic ions. You're going to want to use that chart that is in your lab manual and also in your text. right here. Okay, so it said something hydroxide. I need to know that hydroxide is an OH minus. Okay, so that's why they're telling me this, and that's why this is in a different section, because the polyatomic ions are treated a little differently. So let's do chromium hydroxide is kind of an example. We said hydroxide is an OH minus. I'm acting like this is its own atom. That's what you do with polyatomic ions. They are connected in a different way, and we just kind of leave them by themselves, okay? And my chromium was chromium 3, so Cr3 plus, okay? So I need to find out a way to hook up hydroxide with chromium and balance the charges. So I'm going to need 3 of these because it only has a 1 minus charge, and I need to balance it out with a 3 plus charge. So I need 3 hydroxides to go with 1 chromium. Remember, I write the positively charged metal first, and then for the hydroxide, since it's its own atom, I put it in parentheses, and I put a little 3 behind it. So this is how you write chromium hydroxide, okay? Let's do another one. Let's say it is something carbonate. Where's my polyatomic ions? Let's say ammonium nitrate. If you know, if you ever watched the news or history, ammonium nitrate's like an explosive. Okay, so ammonium, both of these are polyatomic ions that are on your chart. So ammonium is NH4 with a plus charge. Nitrate is NO3 with a minus charge. Double check that. Yes. Okay, so the same rules apply. I write the cation first, ammonium, but I use the name of the polyatomic ion. I don't say nitrogen, tetrahydrogen, nitrogen trioxide, okay? That's why I say it's important to treat the polyatomic ions as their own atom, okay? So ammonium and then nitrate. I don't do the ide either because, like I said, we treat them as their own atom. Okay, now this positive charge will match up with that negative charge and they end up balancing out. So if I write this out in an equation, I would do it probably like this. Okay, it really doesn't matter. You could put them in parentheses, but the fact that I don't have a number behind it, like, let me go back to chromium hydroxide. Did I ever write chromium hydroxide? If chromium had a 1 minus charge, I could just write chromium hydroxide like this. But since there was 3 hydroxides, I needed to put it in parentheses. So that's why the difference in having the parentheses and not, this really has to do with whether or not you have multiple. Okay, if I have multiple, I want to put it behind the parentheses because I want to say I have multiple hydroxides and not multiple. This would say I have multiple hydrogens. Okay, this one right here would say I have 3 hydrogens, while this one says I have 3 hydroxides. Okay, so that's just the parentheses for polyatomics. Okay, so back and forth on the polyatomic ions. It should be good there. This is where we use the prefixes. So di is 2, penta 5. It'd be N2O5. Okay. Yeah, and so it doesn't go into anything more than the tetrahedral on the Vespers stuff. So I think you'll be able to stick with this chart in your text, or they might have one in the lab manual for doing all of these VSEPR modelings. Okay, so you're going to go through. You're going to do the Lewis dot structure like we were doing earlier. You fill in all of your valence electrons, and then you figure out which way to bond it so that you account for all those valence electrons and fill the octet, right? Every atom should have 8 electrons around it in some form or fashion. It can either be tied up in the bonds or it can be in valence lone pairs of valence electrons. But it's important that you have the octet essentially filled in most every case. There's a few of them that are not, and so check yourself on the internet and make sure that you're doing it the right way. Okay, you can look up all of these compounds and it'll tell you what their shape is. And since you're doing all this from home, I kind of almost expect you to do that, but I would like you to be able to do it on your own, figure it out, and then check yourself, and then end up being right. I think you'll be better off if you do it that way instead of getting it wrong and then say, oh, I got it wrong. Why'd you get it wrong? Figure that out. Okay, email me if you have any questions. Use the YouTube videos to touch up on things that you're not really comfortable with just yet, and let me know if you have any other questions or concerns. Okay, so that's it for this week. This is not due until next week. I'll probably make it either next Friday. Not real sure. Look for a due date on the assignments page. Yep, that's it for today. So I'll see y'all. Let me know if you have any questions. Email me over the weekend. If there's certain problems you want me to work and kind of do a practice video, I can do that as well. So I will see y'all next week. Look for your grades, the midterms to be caught up by Monday. If you haven't finished your test, like I said, if you don't do it by Sunday, you need to email me ASAP, and we'll get this figured out and get you taking the test. If you don't have it done by Sunday, it's a 0, okay? That's it. I think I have one person that has like a medical, what do you call it, excuse or whatever. So that's it. All right? I ain't holding off on them no more. All right, y'all. Be easy. Have a good weekend. Stay safe. Go vote if you haven't voted yet. Or go ahead and make sure you're ready to. That's coming around the corner. And I'm proud of y'all. Y'all are doing great. Stay in touch. Let me know where you're at in the course and how I can help if you need any. Okay? See y'all later.